What's up, guys? It's me, Sir Ernest, and today we're going to solve problem 8.20 of Fowles and Cassiday 7th edition. The problem reads, a billiard ball of radius A is initially spinning about a horizontal axis with initial angular speed omega naught and with zero forward speed. If the coefficient of sliding friction between the ball and the billiard table is mu k, find the distance the ball travels before slipping cases occur. So to start with, let's identify the forces acting on our ball. Of course, gravitational force is always present. So this is Fg, and this is equal to mg vector. Also, because of the contact between the ball and the floor, there is a normal force, Fn. If we assume that the object rotates in this direction, therefore the frictional force will be directed in this direction. We know for a fact that the frictional force is given by mu k times Fn. And because there are only two forces acting on the ball along the vertical, and that is the normal force and the gravitational force, therefore the magnitude of the normal force will be equal to the magnitude of the gravitational force. Therefore, this is equal to mu k mg. And this is the one that exerts the torque on this object. And that torque is the one that opposes this motion. If this is our radius and this is the force that exerts torque on the object, therefore the direction of the torque would be out of the pitch. And this opposes the direction of the rotation, which is into the pitch. Hence, the equation of motion for rotation will now be torque equals negative Fk times A. So this is the definition of your torque. Applying our expression for Fk, this becomes negative Uk mga. Newton's law tells us that this should be equal to I omega dot, where I is the moment of inertia of this object and omega dot is the angular acceleration. Because this is a solid ball, therefore the moment of inertia is equal to 2/5 ma squared. Thus, this is equal to 2/5 ma squared omega dots. So therefore, the angular acceleration omega dot will be equal to negative 5 mu kg divided by 2a. Integrating this expression relative to time, we can calculate omega, which is our angular speed as a function of time, and this is equal to omega dot minus 5 over 2 mu kg over a times t. If we want to find the distance the ball travels before slipping ceases to occur, therefore we have to set our limiting case, wherein forward motion is about to start when x dot, which is the forward velocity, is equal to the radius of the ball times omega. If a forward motion is to happen, the equation of motion for the resulting forward motion is mx double dot, and this is equal to the frictional force, which is equal to mu k mg. Now from here, we can solve for the forward velocity x dot by integrating this equation, and this is equal to mu k gt. Here, initially, we set that the object starts from rest. Then integrating this further, we get the distance traveled by the ball, and this is equal to 1/2 mu k gt squared. Therefore, we can rewrite this equation as follows. This is mu kg t is equal to a times omega naught minus 5 mu kg over 2a t. This gives us the time, and this is equal to 2 over 7 a omega naught over mu kg. And finally, substituting this here, we now have our final expression for the distance, and that is equal to 1/2 mu kg times 2 over 7 times a omega naught over mu kg squared. Simplifying this, we now have 2a squared omega naught squared over 49 times mu kg. And this is the distance that the ball travels before the slipping case occurs. So that's it. That's the solution to problem 8.20 of Fowles and Cassiday 7th edition. I hope you learned something today. Thank you guys for watching, and I will see you guys in the next video. Bye bye.